Hello everyone. In this lecture, we're going to cover section 4.8, extreme value problems. Unlike the previous lectures, this is going to be a short one because in this section, we're not going to learn any new theory. We're simply going to apply what we have learned in section 4.4 to real life problems. Remember, in section 4.4, we learned how to optimize a function in the abstract setting. In this section, we will be solving real life problems where we need to optimize a function, meaning what? We're going to be given a situation and we will try to come up with a mathematical model, and then that mathematical model will require us to optimize a function to find the answer, and then we're going to apply the techniques that we learned in 4.4. Okay, so let me directly dive into solving questions. Example. So within, inside a a box in the shape of a right circular cone with radius 1 meter, and height 2 meters, will be placed a a a box in the shape of a right circular cylinder in such a way that the bases of the cone and the cylinder are on the same plane. What is the largest possible volume of the cylindrical box? Okay, so let's read the question. Inside a box in the shape of a right circular cone. So we have a box in the shape of a right circular cone, and with radius 1 meter and height 2 meters. So we're given the radius and height of this cone. So inside this box will be placed a box in the shape of a right circular cylinder. So we have a cone, and inside this we're going to place a cylinder, okay, in such a way that the bases of the cone and the cylinder are on the same plane. So let me draw a picture over here. No, I'm not going to use this. I'm going to draw my own cylinder. So this is my cone. Okay, this is my box in the shape of a right circular cone. A circular cone means that the base is a circle. Right means that it doesn't look like this. When you connect this tip to the center of this circle, which is the base, this is supposed to be a right angle. That's what it means for a cone to be a right cone. Okay. So we have such a cone. I mean, we have a box in this shape, and inside this we will place a box in the shape of a right circular cylinder in such a way that the bases of these guys are on the same plane. So inside this, we are trying to place a right circular cylinder. Okay. Now we're asked to find the largest possible volume of this cylindrical box. How would you approach this problem? First of all, like in the picture I drew, I pretended as if the centers of the bases of these shapes are the same. Why did I do that? Because if you don't align the centers, if you just shift the cylinder, well, what you can do is like pretend that you put a cylinder inside and the centers of the bases are not aligned. So here's the pretend that this is the basis of the cone and this is the basis of the cylinder, and this stays inside. Then by moving this cylinder and aligning the centers, I can move the cylinder and align the centers. Then because in the first place the centers were not aligned, there will be some room for me to actually enlarge the cylinder. So if I am to find the largest possible cylinder, I need to first of all align the centers of the bases. So I'm drawing my shape like this. Okay, and why did I draw this in such a way that this cylinder touches these sides of the cone? Well, otherwise, if the cylinder does not touch, I can slightly enlarge it and I will get a bigger cylinder. So if I am to find the largest possible cylinder, then first of all I should align the centers of the bases, and I should just make the cylinder as large as possible, meaning that its tips over here should touch the sides of this box. Okay. So this is basically like if I want to find the largest possible volume, whatever that volume is, like the cylinder which has that volume will look like this inside this cone. Okay. Now, how do I like? How do I figure out the largest possible volume? Let's say that the okay, I'm given that the height of this cone is 2 meters and its radius is 1 meter. Okay, so I'm given that, and let me call a the radius of this cylinder h and the height of the cylinder. Sorry, let me call this radius r and let me call its height h. Okay, so the volume of the cylinder is volume of the cylindrical box is well, it's pi r square h. Okay, that's the volume formula for the cylinder. Now I want to find the largest possible volume, which means that I want to maximize this function. There is a problem. In this function, I see two variables, r and h. Okay, and I can actually maximize this function, but then I need to use techniques of a 120, Math 120 or Math 118. This is a multivariable function. In future, you will learn how to optimize multivariable functions. So you can actually just like there are some restrictions on r and h, and using those restrictions, you can actually maximize this function of two variables, variables r and h. But this requires you to know calculus 2 techniques, and this is calculus 1. So I'm not going to try to maximize this function of two variables. What I'm going to do is I'm going to try to reduce this. I'm going to play with this function. I'm gonna try to reduce the question to a question of optimizing a function of a single variable. You see, in this picture, like R and H seem as if they are independent, but they are really not that independent because you see the centers of these guys are aligned. I told you that. By similarity of triangles, you can get that. You see, when this radius is 1, this height is 2, which means that a if this length over here is r, this length will be r over 2. Okay, because a tangent of that angle alpha is a 1/2. Okay, so this tells me that this is r over 2, and I know that r over 2 plus h, the total height, r over 2 plus h, the total height is 2. Okay, so this is equal to 2, which means that instead of h, I can write 2 minus a r over 2. Okay, so something is off. Something is off clearly. Well, okay, this is not r over 2. This is 2r. I am being stupid. If tangent of alpha is 1/2, this is 2r. Okay. So h plus 2r is 2. I am sorry for that. So instead of h, I'm going to write 2 minus 2r, not r over 2, because tangent of alpha is 1/2. Okay. So I have that. Now, over here, you see a function of a single variable r. We want to maximize this. Okay. So we wish to. So how did I get this equality from these equations? So we wish to find the absolute a maximum of the function f of r equals pi r squared 2 minus 2r over the interval. Now I found the function that I want to optimize. Now I need the interval. As you can see from the picture, the radius of this cylindrical box can be at most 1, and it cannot be 1 because in that case the height has to be 0, so it would be like simply a cylinder with height 0. It would be a degenerate case, so I want to exclude that. The radius is at most 1, and 1 is not included, like it can't be 1. And the minimum value of the radius is, well, it can be any value greater than 0, and it can't be 0. So the possible values for this radius is, it's in the open interval 0, 1. So I want to find the absolute maximum of this function on the interval 0, 1. At this point, what I have done so far, at this point, I have transformed this real life problem into an abstract mathematical problem, which is what? Find the absolute maximum of this function on the interval 0, 1. The rest is section 4.4. So how do we do that? Let me take the derivative of this. Okay, so this is the function which is like 2 pi r squared minus 2 pi r squared minus 2 pi r cubed. Okay, so its derivative is 4 pi r minus a 6 pi r squared. So in pi r parentheses, it's going to give you 4 minus 6r. So if you set this to 0, you will get one critical point. Like r, if this is 0, either r is 0 or r is 2/3, but r can't be 0 because 0 is not inside this domain. So you get that r equals 2/3 is the only critical point. Okay, and if you draw this picture, this is 0, this is 1, I have 2/3 here, I have one critical point. The derivative over here is a positive, okay, because if r is between 0 and 2/3, like this is positive, this will be positive, so their product will be positive. But if r is bigger than 2/3, then this is positive and this is negative, so this will be negative over here, which means that my function is increasing and decreasing. So I see a local max here, but it's not only just a local max, it's also the absolute max. Why? Well, we've argued this before, but let me argue this again. Like we remember how we optimize functions on open intervals towards the end of section 4.4, we did such examples. I'm going to argue in the same way, as a f prime of r is positive on a 0 2/3 and f is continuous. F is continuous. F of 2/3 is bigger than or equal to f of x for all x in this interval. And similarly, on the interval 2/3 to 1, derivative is negative and f is continuous, so I still have the same inequality holding. Thus, f has its maximum, absolute maximum on a 0 1 at r equals 2/3. So this is the radius which gives me the maximum, which gives me the largest possible volume, and I am asked not the dimensions of the cylindrical box when the volume is the largest possible, but I am actually asked the volume itself. So I need to figure out what f of 2/3 is. So the largest possible volume of this cylindrical box is f of 2/3, which is a 2 pi 4/9 minus 2 pi 8/27 meter cube. Okay, and that's it. Okay, so this is the largest possible volume. So let me solve another question. Example. For this example, I am going to draw a picture for you, and pretend that like this is gonna be water. This is a swimming pool. Okay. So let me draw a diameter for this. Okay. Oops. No, this is bad drawing. I can I am sorry for this. This must be annoying for some of you. Okay. So this will be a 20 meters. Does this actually matter? A No, I don't think so. This is actually a problem from your book. So let me take a look. Yeah, let's put this as 20 meters. Okay. So a man is standing here at this point A, and this is the point B. Okay. So a man is standing on the edge of a swimming pool in the shape of a circle. Okay? A At point A as shown in the figure. Okay? He wants to a go to the point B as quickly as possible. Okay? And I should give you the information that the line segment AB is the diameter of the circle, where a this line segment AB is the diameter of the pool. Okay. A What route? Given that this man can run twice as fast as he can swim, what route should he take? Okay, so we have a swimming pool with a man standing on the edge, and he wants to go to the opposite side, and he can run twice as fast as he can swim. Okay, and he wants to go there as quickly as possible. What route should he take? Okay, let's think about this. So what can he do? Well, he can just run all the way over here. First of all, okay, let's see what he can do. He can just run in some weird route like this. Okay, but then that wouldn't be optimal because, well, he's just taking unnecessary, like, he's just taking a route which is longer than it's supposed to be. So instead of doing that, what he can do is he can just run on the edge. So he can do that. Or he can directly jump into the pool and swim towards me. Or what he can do is he can just run some of this. He can run on the edge for some time, and then he can jump and he can swim the rest. The question is, what is he supposed to do? Like, by the way, he can swim and any way he wants. He can swim like this, but if he's not swimming towards B, he'll lose time. So if he wants to go as quickly as possible, wherever he jumps into the water, he should directly swim towards this point B. Okay. So what should he do? So he can run twice as fast as he can swim. So that means you may think at first sight that, okay, then if he's running faster, he should just run. But the problem is he's going to be running in a circular path, which is which is longer than a direct path where he can swim. So you may not think that, okay, then, well, if that path is more direct, like if that path is shorter because it's more direct, maybe he should just jump in and swim. But he's not swimming that well, is he? His swimming speed is the half of his running speed. So maybe he should just run for some time and then jump to the pool and then swim. So what should he do? That's the question. We're supposed to figure this out. So first, let's observe the following. Whatever he's going to do, if he's running, he should be running on the edge of this pool. Otherwise, if he's taking unnecessary paths going all the way around, he's going to lose time. So if he's running, he should be running on the edge. That's the first thing. That's the first observation. The second observation is if he ever decides to get in the pool, after he gets in, he should be swimming directly towards the point B. Otherwise, if after jumping in, he's just making some circles and swimming in some curved path, then he'll lose time as well. So the second observation is if he jumps into the pool, from that point on, he should be directly swimming towards the point B, meaning that his path, his swimming path should be aligned from the point he jumped in to the point B. So whatever his optimal route is, whatever his optimal route is, it's going to look like, okay, I think I need to select this every time I'm doing something. Okay, so this is the point B, this is the point A. Whatever his optimal route is, because of these two observations, it's going to look like that. Maybe he ran some of this way, and afterwards he decides to jump in. And after he jumps in, he should swim directly towards the point B. Okay? So roughly, his route is going to look like that. We're trying to figure out where he should jump in. Okay, so let me mark the center of the circle, and let me call this angle alpha. So wherever he's jumping in, let's call this point C. The angle COA, I'm calling it alpha. We're trying to find the optimal value for alpha. Alpha may be 0, meaning that if alpha is 0, he's not running at all, he's directly swimming. Alpha may be pi radians, meaning that he is just running all the way, okay? And if he decides to jump into water right in between, alpha would be some value between 0 and pi. So this is like 10, this is 10, and this is 10. Let me write down the function which will give his his travel time. Okay, so let me call this a arc length K. And let me call this L. Okay? So, we don't know what K and L are. The total travel time, will be, okay, he can run twice as fast as he can swim. So I'm just going to pretend that his running speed is 2. I'm not gonna specify any units, okay? I mean, if you want, I can give some units in the question. I can say that he can run like 2 meters per second, and he can swim 1 meter per second. Maybe I should do this. Given that this man can run 2 meters per second and can swim 1 meter per second, what route should he take? So if this arc length is k meters, it takes for him to like, in order for him to reach from point A to point C, he should spend k over 2 seconds, and then he's gonna swim all this way, L meters, with speed 1 meter per second. So this is his total. This is his total travel time. Okay. Now let me try to figure out what K and L are in terms of alpha, because it seems as if K and L are like two independent variables, but then this would be a function of two variables, and I don't want to optimize such a function because I don't know how. So I need to turn this into a function of a single variable. And from the picture, we can actually guess that everything will be depending on alpha. So let me try to write a K and L in terms of alpha. Now, the circumference of the circle is 2 pi 10. And he is running how much of this? Alpha over 2 pi of this, okay? Because the full circle is 2 pi radians, and I'm assuming that he's running for alpha radians. So this is K, okay? Now for L, I have to do some geometric arguments in order to compute L. Now, because this is 10 and this is 10, this angle is alpha over 2, and so is this angle. But now, if you just draw this right triangle, you can actually see that let's call this D. The line segment CD has length 10 sine alpha, okay? So this is 10 sine alpha, because this divided by 10 is supposed to be sine alpha. But I also have that this length divided by L is sine of alpha over 2. If you just look at this big right triangle, CD divided by L is sine of alpha over 2, which means that, okay, I'm going to use the half angle formula. So I will have 10 times sine alpha is 2 sine alpha over 2 cosine alpha over 2, and this divided by L is sine alpha over 2. Okay, and I am going to cancel these and then get a cosine alpha 2, get L as a 20 cosine alpha over 2. Okay, so L is 20 cosine alpha over 2. And this is my function now. This is a function of a single variable. So we wish to minimize f of a alpha, which is the function. Let's cancel these. 5 alpha plus 20 cosine alpha over 2 over the interval. Well, the interval is 0 pi because in this case it is possible that directly maybe the optimal way, the optimal route is him directly, like is obtained by him directly swimming, in which case alpha would be 0. Or maybe the optimal route is obtained by him running all the way, in which case alpha would be pi. So now I have a closed interval. Okay, so how do I opt? Now, at this point, I have turned this question into an abstract optimization question. I have a function of a single variable. I want to optimize this over the closed and bounded interval. So what do? I find critical points, I find singular points, I find endpoints, I plug these in. The maximum will give me the maximum value will be the absolute maximum. Okay. So I want to maximize this. So what is f prime of alpha? It's 5 plus 20 times derivative of cosine is minus sine, so I have minus sine alpha divided by 2 times derivative of inside is 1/2, so it's going to give me a 5 minus 10 sine alpha divided by 2, and if you set this to 0, you are going to get that sine alpha over 2 is 1/2, which means that alpha over 2 is a pi over 6, and well, it's not just a pi over 6, it can be pi over 6 or 5 pi over 6 and so on, like the angles which give you sine 1/2, but if alpha is between 0 and pi, alpha over 2 should be between 0 and pi over 2, and the only angle between 0 and pi over 2 whose sine is 1/2 is a pi over 6, so alpha over 2 is pi over 6, which means that alpha is pi over 3. Okay, so this is the only critical point, and this interval 0 pi. And now I plug in the endpoints and I plug in the critical points. There are now singular points, as you can see. So I plug these in. If you plug in 0, you are going to get 20. So it takes 20 seconds for him to go there. If you plug in pi over 3, you're going to get 5 pi over 3 plus 20 cosine pi over 6. This will be 20 cosine pi over 6 as a root 3 over 2. So you have 5 pi over 3 plus a 10 root 3. You have that. And if you plug in pi, you're going to get 5 pi plus cosine pi over 2 is 0. So you're going to get a 5 pi. Now I should compare these. Unfortunately, I'm gonna get some help for it. Let me take some guesses here. Root 3 is something like 1 point. 1 point. Something is off here. This is 1.7. Something like 1.7. Blah blah blah. So this is gonna be around. This term is gonna be around like it's gonna be something like 17. But this is greater than 1, so this is gonna be greater than 22. Okay, apparently, just let me take a look at something. No, that's fine. That's fine. I mean, there's nothing wrong. I thought for a second that the optimal way for him was to actually run some of the route and then swim the rest, but apparently that's not going to be the case. So this is like 1.7. This is bigger than 1, so this is actually bigger than a 22. You can actually check that. So this is something around a this is something around 15 point blah blah. So this is clearly less than 20. So the least number here is this. So so to in order to minimize the travel time, this man should run all the way a on the over the edge. Okay, so it turns out that he should just run all the way because the alpha, which minimizes this function, turned out to be pi, which means that he should just run all the way. But if well, okay, that wouldn't be a nice, like that would be a stupid question. But if someone asks what's the route that maximizes the travel time, that would be him running for a pi over 3. That would be him running until the point which makes the angle alpha pi over 3, and afterwards he should swim. In that case, it would take over 22 seconds for him to go there. Okay, that would be the max. That would be the path which maximizes the travel time, which is what we want. Okay, so that's that. I'm sorry for hesitating. Like when I started I picked the question ahead of time, but I didn't actually solve it ahead of time. I just wanted to solve it with you. So I thought for a second that the answer would be that like he runs some of the way, then he swims the rest. Apparently, no, he should just run all the way. Okay. So one last question, and then we're gonna stop. So this is yeah, we found the absolute minimum of this function. One last question. This is again one of the exercises in your book. A example. Find the shortest distance from the origin to the curve. X squared y to the power 4 equals 1, and I'm gonna pretend that x and y are both positive, okay? I don't have to do that, but I will. So, I have a curve in this question, which is defined by the equation x squared y to the power 4 equals 1. And I'm gonna I'm told that like I should consider the parts of this curve has parts in all 4 quadrants, but I'm supposed to consider the parts in the quadrant I'm supposed to consider the part in the first quadrant where x and y are positive. So let's try to understand what this curve is. If x squared y to the power 4 is 1, then y is 1 over root x. Okay, if x and y are both positive, so it's going to be a curve which looks like this. Okay, so x squared y to the power 4 is 1, and if x and y are both positive, what you can do is you can just put x squared to the other side, and you will get y to the power 4 equals 1 over x squared, and then you will take the fourth root of both sides. Because everything is positive, what you're going to get on the right left hand side is going to be y, not absolute value of y because it's already positive, and on the right hand side you're going to get 1 over root x. Okay, so this is my curve. I want to find the shortened distance from the origin to this curve. Okay, so here's my origin, and I want to find the shortest distance. So you see that there will be some point on this curve which minimizes the distance. Okay, why? Because if you just move this point in this direction indefinitely, the distance will go up to infinity. And if you move this point in this direction indefinitely, the distance will go up to infinity. So there should be, like, intuitively you're seeing from the picture that there should be a point which minimizes the distance. Later on we will mathematically show that this is the case, but at least from the picture we're guessing that, okay, there is some point in between which is closest to the origin. Okay, so let me pick up an arbitrary point on this curve, and let me call its coordinates, well, its coordinates are x, let's pretend that its coordinates are x and y. Okay, the distance of the point xy on this curve to the origin is d equals square root x minus 0 squared plus y minus 0 squared, and I close the square root by the distance formula. Now, instead of y, I can write, like, this is a function of two variables. Okay, and I don't want to try to optimize a function of two variables. Just like before, I need to reduce this to an optimization problem of a function of a single variable. So I'm going to either try to write x in terms of y or y in terms of x. So let me write down y in terms of x. If I write instead of y 1 over root x, then I'm going to get x squared plus 1 over x. Okay, so this is my function. Now, there are two things that I can do at the moment. I can directly try to optimize this function over a certain interval, or I can try to optimize its square. Okay, which is a trick people often do. So I'm just going to do that and explain why I can do this. So we wish to find the absolute minimum of the function f of x equals square root x squared plus 1 over x over the interval 0 to infinity. Okay, so we can do that just like before. We can do this just like before, or we can try to find the point which maximizes the square of this function, which is x squared plus 1 over x over 0 to infinity, because yes. Okay, let me first write down a reason, then I'm going to explain why this is the case. Because f of x is a positive on this interval. Okay. Now, what people often do is when they try to optimize a distance between 2 points, instead of trying to find the maximum or minimum of the distance, they try to do the exact same thing for distance squared. And there is a reason that this approach works. The reason is, okay, the distance by definition takes positive values, right? Unless you're on that exact same point, it takes positive values. Okay, so I'm giving you some positive values, okay? Finitely many, infinitely many, I don't care. One of them is, pretend one of them is the maximum and one of them is the minimum. Okay, that's fine. You square everything. If you square everything, which number gives you the maximum now? The exact same number. Because if A is less than B, and if A and B are positive, A squared is less than B squared. So if you're dealing with positive numbers, if A and B are positive numbers such that A is less than B, A squared is less than B squared. Okay? Because x squared is an increasing function. Now, for this reason, if you have a bunch of numbers, and if one of them is the maximum and the other one is the minimum, when you square everything, like if you look at the maximum minimum among the squared numbers, the ones that will give you the maximum minimum will be the same as the old ones. Okay, what this means is, instead of trying to find the point which gives me the absolute minimum of the distance, I can actually try to find the point which makes distance squared a minimum. Why do I want to do that? Because like if you're dealing with such problems, find the distance of blah blah to blah blah in the plane or in the space and so on, the distance formula has a square root in it. Yes, like you can see it over here. It has a square in it. Okay, do you really want to take the derivative of some expression with square inside, a square root inside? No, I mean, the distance formula, did I say square? I am sorry. The distance formula, it has square root at the beginning of it. And if you try to take the derivative, you will end up having some term like 1 over 2 root blah blah times blah blah. You don't want to do that. It just makes things uglier, okay? So instead of doing that, you can actually try to optimize distance squared. So that's what I'm going to do. Because as you can see, when I compute the distance squared, it's just a nice function. So let's call this g, and let's take the derivative of this. It will give you 2x minus 1 over x squared. Okay? And is something off here? No. Yeah. Let's set this to 0. Let's make this 0. Let's pretend that g prime of x is 0. In this case, you get that 2x is 1 over x squared. So you get that x cubed is a 1/2. So x is 1 over cube root of a 2. Okay? And if you draw this table that we've drawn over and over again, you'll see that this is the critical point. There are no singular points inside the domain. I mean, there is a point where the derivative is undefined, which is 0, but it's not in the domain. So you have that, and you see that this derivative is positive over here and negative over here and positive over here. Okay, so my function is decreasing and increasing. As before, one can argue that it's just like the first question. I have an interval, I have one critical point, over here is increasing and decreasing. This point not only gives me a local maximum, it actually gives me the absolute minimum. Just like that, you can actually argue that this point is not only this point, at this point 1 over cube root of 2, you not only have a local minimum, you actually have the absolute minimum. One can argue that G has its absolute minimum. Its absolute minimum at x equals 1 over cube root of 2. So the shortest, well, what was the question? Shortest distance. The shortest distance of the origin to this curve is obtained at this point, 1 over cube root of 2. Now, as you can see, I'm plugging this into f, not g, because g is the distance square, okay? The actual function which gives me the distance is f, so I'm going to get 1 over a cube root of 4 plus cube root of 2, so I get this very ugly number, whatever this is, okay? So that's it. Okay. So maybe I should say the following. One can argue that G is absolute maximum blah blah. So I'm just gonna say that this is an exercise to you. So argue that this has its absolute minimum at this point. So I'm gonna say that this is exercise because I was too lazy to write it down. Okay. And that's it. This is the point which gives you you can actually find the point which gives you the shortest distance. Its x coordinate is 1 over cube root of 2, and you can find what its y coordinate is. It's going to be 1 over square root of that number, whatever it is. And the shortest distance is this ugly number. Okay. So what have we done today? We've solved 3 optimization problems, which are not abstract optimization problems, but they're real life problems. And in each of these, we first had to mathematically model the situations to reduce these problems to abstract optimization problems, like find the maximum of the blah 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 function on the interval blah blah. Find the minimum of the function blah blah over the interval blah blah, and find the minimum of the function blah blah over the interval blah blah. So you take your real life problem, you model it, and then you turn it into an abstract optimization problem. Then you apply the techniques that you learned in 4.4. Okay. Okay, so that's it for today's lecture. Stay safe.